Greeting to everyone. My name is Peyman Behna. I'm a first-year PhD student at Georgia Tech. Today, I'm going to talk about our recent work, forms, fine-grained, polarized, ReRAM-based in-situ computation for mixed-signal DNN Accelerator. This is joint work with researchers from Northeastern University, Samsung Semiconductor, Stevens Institute of Technology, University of Southern California, University of Utah, and University of Connecticut. DNNs are the state-of-the-art solution for many applications. However, there are some challenges with DNN computing. First is that to satisfy the increasing complexity of DNN tasks and ensure high accuracy, the DNN model size becomes larger and larger, and the required storage and computation becomes very huge. Second is that the primary source of energy consumptions in today's computer system is data movement. As an example, the total energy required for fetching two operands from the main memory to an ALU is 200x higher than the energy required for performing an addition in the ALU core. So the conventional CMOS-based DNN accelerator are no longer sufficient to meet the requirement of the increasing storage and also low latency demand of modern DNNs. One of the promising solutions of the mentioned challenges is incorporating PIM with emerging memory technology such as ReRAM. The reason is that ReRAMs have zero leakage and refresh power, high integration density, and non-volatility. In addition, ReRAM-based DNN accelerators can perform efficient in-situ vector matrix multiplication, which is the core of DNNs. Prior work such as Isaac, Prime, PipeLawyer, Puma, and Timely show promising results of using ReRAM engine in assorted DNNs. However, the existing solution suffer from major problems. First, mapping sign weights. Current architectures either decompose crossbars to positive and negative ones like prime, which lead to a significant crossbar overheads, or they add an offset to the original negative weights value to make all of them positive, like Isaac. In this case, since the bitline output represents a sum of product with bias weights, we need to convert the result. So for each negative value, which is distinguished by ones in the MSB position, we need to add a bias, and at the end, we need to subtract as many biases as the ones in the input. This leads to peripheral circuits overhead. Second, existing solutions perform coarse-grained computation using coarse-grained crossbar. There are several drawbacks here. A, the current deviation on the bit line when we active so many word lines like 128 or 256 lead to overlap with neighboring state in the accumulated current distribution, and as a result, the accuracy will degrade. B, C, and D are that we need to use ADC to convert the value from analog to digital. They actually consume significant area and power. When the number of active rows in the crossbar increases, the accumulation sums become larger. So we need larger ADCs. The area and power of ADCs increase exponentially when they become larger. So the current architecture usually uses one ADC per crossbar. However, in this case, one ADC needs to swap so many columns like 128 or 256 in a short amount of time at a high speed. For example, in case of Isaac, one ADC needs to convert the current of 128 columns in less than 1 nanosecond, which is hard in practice. Finally, the ADC used in ISAC and many other follow-up papers is a special case. If you look at the datasheet of other off-the-shelf ADC, you see that the area and the power of Isaac ADC is even less than 6-bit or 4-bit ADC. The reason is that this specific ADC is fabricated with IBM technology. They have access to a special technology where they can place deep trench capacitor buried in the oxide vertically. This is exclusive to only IBM and not common at all. In general, the area and power of 8 or 9-bit ADCs are much larger than the one used in the ISAC. The third problem is that the existing architectures offer high throughput but low frame per second processing rate. The reason for having high throughput is that they usually activate so many word lines at the same time, which is not practical as I mentioned before. Also, their FPS is very low, while many applications like object detection, self-driving cars, and AR, VR take advantage of a very high frame per second. The first problem is that they are software optimization agnostic. They don't pay attention to existing software optimization approach like mapping, pruning, quantization, and even intrinsic sparsity of current DNNs. Some of them do some optimization to utilize sparsity, but they are mainly hardware managed with remarkable overhead such as row indexing, routing controls, word lines control, etc. Like for example, RECOM in date 18 or SRE in ISCA'19, or they are highly model dependent like SNRRAM in DAC 18. Our solution to solve the mentioned challenges is FORMS, which is an algorithm hardware co-design solution. I'll explain the details in next slide. First, we do pruning. Forms combines two types of structure pruning method, filter pruning and filter shape pruning. The filter pruning removes the weights on the entire filter, where the filter shape pruning removes the weights on the same location of all filters. As we know, the weights in a convolutional layer can be considered as a 4D tensor as shown on the left-hand side of the figure. We can reshape them to 2D weight matrix representation as shown on the right-hand side of the figure. Each column represents all the weights from the same filter and each row represents the weights on the same position of all filters. The filter pruning and the filter shape pruning remove the column and row from the weight matrix respectively. After pruning, the remaining weights can be performed and changed to a smaller weight matrix with a regular shape. This can reduce the hardware cost by reducing the number of crossbar to accommodate all the weights. Second, we do polarization. In forms, the weight in a fragment are polarized with the same size. In fact, fragment means part of a column with the same size. They are either positive or negative. There are two challenges here. First is that how to determine the sign of the weights in a fragment, and the second is that the mapping policy of weights to subarray columns. To achieve weight pruning, polarization, and quantization at the same time, Our work incorporates the alternating direction method of multiplier or ADMM into our training process to obtain high quality, prune, polarized, and also quantized model with our specific constraint. ADMM is basically an advanced optimization technique which can decompose a DNN training and specific model optimization problem into some sub problems that can be solved separately and iteratively. ADMM regularization can reforge and then separate the problems, then solve them iteratively. Due to interest of time, I skip the details of ADMM regularization. You can refer to our paper for more technical content. With that, we examine how large can be a fragment size. As the result for CIFAR 100 shows, for the evaluated DNNs, there is no accuracy drop with appropriate fragment size, like for example, 8 or 16. There is a minor accuracy drop when fragment size is 32. When the fragment size is larger than 32, the accuracy will drop considerably. That shows that the coarse-grained computation cannot be incorporated into our framework. The optimized ReRAM-aware DNN model is obtained from ADMM-regularized optimization. For each fragment, an associated 1R is used to store the gain. Form utilizes coarse-grained crossbar but fine-grained computations. As a result, we have smaller ADC that of course saves the area and power. We can use more ADCs per crossbar that compensates throughput drop because we use smaller ADC and we activate fewer word lines compared to coarse-grained computations. Fewer columns need to be swapped by each ADC. And of course, it is more practical for fabrication. Besides, it provides more opportunities for utilizing sparsity. For example, forms have a low overhead, zero skipping logic. Generally, existing architectures need 16 cycles to feed a 16-bit input to the crossbars. However, most inputs actually have smaller value and can be represented by just a few bits, which means the upper bits are all zeros and can be skipped from feeding to the crossbars. Larger crossbar, for example, like ISAC, have higher probability to contain at least one input that is significant bits are not zero. Zero skipping logic with negligible overhead incorporation with, for example, a small fragment size and fine-grained computation can cache the intrinsic sparsity of DNN models. Zero skipping saves required feeding input cycles. For example, this plot shows the average effective input cycle for various fragment size of different layers of ResNet 50. As you can see, when the fragment size is smaller, the average effective cycle are smaller. We observe kind of the same trend with other DNNs over different datasets as well. Okay, let's look at our experimental setup. For training, we use 8x NVIDIA Quadro RTX 6000 GPU by PyTorch API. We use MNIST, CIFAR 10, CIFAR 100, and ImageNet dataset. For DNN models, we are using LeanNet 5, BGG16, ResNet 18, and ResNet 50. We tried different baseline for our software experiments like NeurIPS 15, ICCV17, DAC17, ECCV18, NeurIPS 18, CVPR19, and ASP DAC20. For our design space exploration, we developed enhanced tool while its backend utilizes unified Cacti 7 NVSIM and NVSIM CAM with efficient interconnections and with multi-banking support. Also, we developed enhanced tool while software results are back annotated to the hardware to basically reflect the amount of optimization that we did in the software part. And we basically chose digital and also mixed signal hardware baseline. For digital, we used DNN, TPU, WAX, and Simba. And for mixed signal, we tried Isaac and Puma. So here we show the result for CFAR 10. So in summary, by combining the fragment polarization and quantization, our overall crossbar reduction ratio is 2x higher than tiny but accurate with similar accuracy compared with the original baseline model using a split mapping scheme that basically it has positive crossbars and also negative crossbar for positive weights and also negative weights separately. So here is the same result, but for CFAR 100 and also for ImageNet. For CFAR 100, without accuracy loss or with minor accuracy loss, we achieve 53x and 73x and also 65x crossbar reduction on ResNet 18, ResNet 50, and VGG 16 respectively. For ImageNet, compared to tiny but accurate, we achieve higher crossbar reduction like 13x and 16x with higher or similar accuracy when fragment size is 4 and 8. Since model accuracy is more sensitive to pruning ratio on ImageNet dataset, to achieve a higher overall weight reduction ratio and maintain model accuracy, we use a less aggressive pruning strategy in the case of ImageNet. Here, we show the hardware results for our basically architecture, which is form, and also for the Isaac and DNN. Here, to have a fair comparison with Isaac and DNN, we choose an ISO area approach. So here we show the experimental result for area and power efficiency. Forms outperform existing architecture when we apply all the proposed methods. For example, when fragment size is 16 in terms of GOPS per second per millimeter square, forms outperforms the original non-prune Isaac and prune quantized Isaac by 36x and also 1.x respectively. In terms of GOPS per watt, 51 and 1.9x improvement compared to the Isaac and pruned quantized Isaac respectively are gained. These plots show frame per second speed up for CFAR 10. As it is clear, applying pruning and quantization will speed up the frame processing rate of Isaac by 160x and 200x for VGG 16 and ResNet 18, and apply pruning and quantization increasing forms speed up to 109x and 155x when fragment sizes are 8 and 16 respectively. By applying zero speaking on top of model optimization, the speed up of forms goes up to 375x and 366 when fragment sizes are 8 and 16 respectively. Here we show the same result but for CFAR 100 and ImageNet. Since the prune ratio for ImageNet is less than the other dataset, frame per second speed up will be less compared with CFAR datasets. Forms still outperforms original Isaac by 11x in worst case scenario. In conclusion, I would say Forms proposes fine-grained ReRAM-based DNN accelerator with algorithm hardware co-design optimizations. Weight pruning and quantization techniques are combined to explore a good balance between the overall hardware cost and performance. Existing architecture with coarse-grained computation can enjoy the proposed pruning and quantization techniques. And a novel fragment polarization method is proposed to elegantly solve the natural challenge of representing sign weights. And we know that the algorithm hardware is a key of designing new mixed signal hardware accelerator. Thank you. See you during our Q&A sessions.